So here we go back to the recursion relation, and remember that we basically said that e squared lambda should be equal to 2n. So that means here in the denominator we have minus 2n plus 2 times k plus l plus 1. So we can rewrite the recursion relation as ck plus 1 over ck is equal to 2 times k plus l plus 1 minus n over all that junk, k plus l plus 2 times k plus l plus 1 minus l times l plus 1. And I'm not going to do the multiplication here to show that. I'll leave it to you to convince yourself of this. But the denominator can be rewritten as k plus 1 times k plus 2l plus 2. So you just multiply that out, multiply that denominator out to see if all the terms are exactly the same. What's that? No, I'm saying, it's tedious, but you expand this all out. You expand this all out, and you find that the polynomials that you get are exactly the same. I'm taking the denominator here in this expression.
The e squared.
Yeah, e squared lambda is 2n. Remember, that was our condition for the termination of the series was e squared lambda is 2n. So we can also write the recursion relation like this, and I'm bothering to do this because it's the form that's in your book. ck plus 1 over ck is equal to 2 times k plus l plus 1 minus n divided by k plus 1 times k plus 2l plus 2. Which is equation 476 from your text. With, by the way, j going to k. Your book calls the subscript j what I call k, but subscripts are just names anyway. So your book says cj plus 1 over cj is 2 times j plus l plus 1 minus n over j plus 1 times j plus 2l plus 2. I've been calling it k, the book calls it j, tomato, tomato, let's call the whole thing off. Okay. Now I sound like a guy on the cell phone. Okay. All right. So you get to apply the recursion relation in the homework. It's all highly entertaining. It's good for the soul.
Good for the soul, bad for the wrist.
It's sleep-inducing. Yes. Well, see, you need more sleep, so I'm just trying to help you get to sleep. Right. Yes, it's like, it's a little bit of mathematical power. Okay, so. Let's see. So. No, that's not the. 119, 118. Yeah. Okay, so anyway. So the series terminates at, as we said, k max equals n minus l minus 1. So in terms of n, in L, the series terminates at c sub n minus l minus 1. That's the last term, the one that has that c sub k. Okay, so VEL, if you go back, VEL is rho to the L plus 1 sum from k equals 0 it terminates at k max, so to n minus L minus 1. So we started with k equals 0 to infinity, but then we found out, no, it stops at some k max, which is n minus L minus 1 of c sub k rho to the k. And thus, V sub EL is rho to the L plus 1 times a polynomial of degree n minus L minus 1. Called a Laguerre polynomial. And I'll leave it to you doing the homework to see a little bit more about lovely properties of Laguerre polynomials and associated Laguerre polynomials and all that sort of deliciousness. So overall, VEL is a polynomial of degree what in rho? What's the highest power of rho that appears in this polynomial? N, right? Because the highest in the summation is rho to the n minus L minus 1, and then I multiply by rho to the L plus 1, and so I get rho to the n as the highest power that appears in that polynomial. So VEL is a polynomial of degree n in rho. And then working backwards, then UEL, which we said define VEL via UEL as e to the minus rho VEL, is e to the minus rho times a polynomial of degree n in rho. So now our e to the minus rho has come back into the picture. That was there all along, but we've done a transformation to temporarily get rid of that asymptotic behavior, or at least to not get rid of it, to make v exhibit how the function differed from its asymptotic behavior. And, that's getting too low for me to write clearly, and what we really started with was REL, when we separated the variables in the wave function. So, REL, we defined UEL that REL was UEL divided by R. So that says that REL is e to the minus rho times a polynomial of degree n minus 1 in rho, because rho and r are proportional to one another. Rho and r are just a constant times one another. So still I've got it as a polynomial in rho, but it's also a polynomial of degree n minus 1 in r as well, because we had said, as I'm sure you remember, I probably don't even have to write this, but as I'm sure you remember, rho was defined to be the square root of 2mw over h bar squared times r. So rho and r are just proportional to one another. But that's equal to, now that we know the expression for the w's, for the energies, that's equal to 2m over h bar squared, m over 2h bar squared, e squared over 4 pi epsilon naught 2m over h bar squared. W is the rest of all of this stuff, with no minus sign, because remember, W is minus the energy, and is therefore positive, times R. All of that is still times R. Simplify a little bit, and that's 1 over n times me squared over 4 pi epsilon naught h bar squared times R. What do the units of that quantity, this middle term here, what do the units of that have to be? Well, note that rho is appearing as the argument of an exponential. Now, what do the units of the argument of an exponential have to be? Unitless. It needs to be unitless. So rho is dimensionless. So therefore, what do the units of this have to be? What is n? It's an integer, no units, right? What are the units of r? Length. So what are the units of this quantity? Right, reciprocal length, right? And we call that 1 over a. So this is equal to, by definition, r over n a. So a is, 1 over a is this stuff right here. A is known as the first Bohr radius. And guess what it's equal to? Even though it doesn't have a right to be. It's the radius of the ground state orbit in the Bohr model. When you do the Bohr model, the radius of the ground state orbit is me squared over 4 pi epsilon naught h bar squared. Shows up in our expressions for the wave functions of the hydrogen atom, because that exponential and the polynomials which show up, these polynomials in rho times e to the minus rho, involve r over na, involve r over the Bohr radius times 1 over n times the principal quantum number. How big is the Bohr radius? Remember? About half an, yeah, half an angstrom. Yeah. It's 0.55 angstroms, about half an angstrom. 1 angstrom being 10 to the minus 10 meters, a tenth of a nanometer. So that's the characteristic size of an atom. It's about an angstrom. Why? Because when you do the quantum mechanics for the hydrogen atom here, and then other atoms are in general terms similar, it shows up in the expressions for the radial part of the wave functions as a characteristic distance scale. So that, now we'll just call it Rnl. We called it Rel before, but now we know E is determined by the principal quantum number, so let's just use n as the subscript. Rnl of R is equal to e to the minus rho, but that's e to the minus r over na times polynomial of degree n minus 1 in r over na. Since rho is r over na and it's a polynomial of degree n minus 1 in rho, it's a polynomial of degree n minus 1 in r over na, or in other words, fundamentally of degree n minus 1 in r. So the radial part of the wave function is e to the minus r over na times a polynomial of degree n minus 1 in r. That's the grand high thing that comes out of all of this. And then you get to grand highly find some of, do some things with that in the homework. But let me here just show some of them. So the book gives you a table of them. Let's see. So for this to work best, I should probably do several things. 1, turn on the projector. 2, leave the lights on so that nobody falls asleep. 3, realize nobody can see the screen, so therefore turn the lights off anyway. 4, talk very loudly so that nobody falls asleep.
5, scare the class out of the switch.
That's right, yes.
So that thing won't fall asleep. Yeah.
Right, yes. And now hit the right one. No, stop. There you go. All right. And no vision. Wait a moment, please. Okay. Let's see. Slideshow. From the current slide. Now, I probably have to do the function. F7. Oh, 6. Connect video cable to projector, or from laptop to projector. That would be the next step. 7, curse under my breath. 8, rejoice in seeing image on screen. 9, actually turn the lights off as threatened before. There we go, something like that. Okay, so, yeah, I'll go ahead and turn Alex's attention to the screen. Oh, look at that. Isn't it beautiful? I agree. Oh, yeah. Nice. All right. That is the most exciting slide I've seen in the last several seconds. All right. So, there you go. Memorize the ones down. You just memorize down to R3's. Okay. Table. Let's see that it does what we claim it does. So, for pointer, 2-meter stick pointer. So, R10 should be e to the minus r over 1 times a, because n is 1, times a polynomial of degree n minus 1, which is 0, right, because n is 1 here. A polynomial of degree 0 in R. What's a polynomial of degree 0 in R?
1.
Yeah, constant, right? It's just a constant. So this is just the overall normalization constant set by normalization of 2a to the minus 3 halves e to the minus r over a. So that's the radial part for the ground state wave function for our hydrogen atom. R20 and R21 should both be e to the minus r over 2a times a polynomial of degree 2 minus 1 equals 1 in r over a. And so there we have it. We're just plain r. So here's a polynomial of degree 1, namely 1 minus 1 half r over a. Here's another one of degree 1. This was just r over a. And on and on and on. R30 is e to the minus r over 3a. Polynomial of degree 3 minus 1 equals 2. So these are all second degree polynomials. They're just written in terms of r over a, but you could make them in terms of r over 3a if you wanted to, but then you would just change the constants out in front in order to compensate for that. So they usually just leave it as r over a for the polynomials. So they behave as claimed when you look at them. And here are plots of those RNLs, all on top of one another to make it maximally confusing. But nevertheless, here is our 10 plotted. Note that it blows up as you approach the origin, but by doing one of the homework problems, you will deduce that that doesn't mean that the particle is most likely to be found at the origin, because the probability of finding it in some spherical shell of thickness dr is wave function psi times the volume of the shell, 4 pi r squared dr. And that factor of 4 pi r squared goes to 0 as you go to the origin. So in fact, the maximum probability density is somewhere in between. And you'll figure out where that is. Here's R2, 0, R3, 0, R3, 1. The thing I'll call your attention to is that the number of radial nodes is equal to n minus L minus 1. So for example, it's n minus L, or not, I forgot. N minus L or n minus L minus 1?
Or is it n minus L plus 1?
I don't know. Well, let's figure out for one of them. So let's see. Here's for R31 here has 1 radial node, and yeah, and then 3 minus 1 minus 1 is in fact 1, so that works out. R32 has no radial nodes. It's 0 at the origin. We don't count the origin. 0 at the origin, 0 at infinity, nowhere in between. So other than the origin, how many radial nodes? 3 minus 2 minus 1 equals 0. And if you look at these carefully, it always works out that the number of radial nodes is n minus L minus 1. And do I want to say more? Okay, well, so then you couple it with this, the YLMs, and this is from Wikimedia. User Poor Leno created these basically density plots for hydrogen wave functions. These are the physicist version of the hydrogen wave functions, where we use spherical harmonics that are eigenfunctions of the LZ operator, so that their angular dependence is e to the im phi. They're not the ones that chemists like to use. I'm going to give you a homework problem which shows you how to make the chemists' version of the angular wave functions. They prefer real angular wave functions over imaginary ones. Theirs are not eigenfunctions of L sub z in general, except for the ones that have L sub z equals 0. But they have the advantage that they look like one another, and that they're kind of more natural to use if you're going to look at the wave functions which show up when you want to create chemical bonds. So they don't care about eigenfunctions of LZ so much as wanting things to look symmetric and all chemical bondy, so to speak. Here's a plot, an image from your book that shows surfaces of constant probability density for various hydrogen wave functions. And here's another version of that from Wikimedia for the n equals 3 hydrogen wave functions. These are surfaces of constant probability density, and so you get a different surface depending on what particular value of the probability density that you pick. And these are color-coded colors of the rainbow to indicate the phase of the e to the I phi part, because that's the of the e to the I m phi part. That's the complex part of the wave function. The associated Legendre function is real valued in the YLMs, and the R and L functions are real valued. So all the complex part comes from the e to the I m phi part of the wave function, the part that makes it an eigenfunction of the LZ operator. So if m is equal to 0, what is e to the I m phi if m is equal to 0? 1. So this all has the same phase. It's a real function in that case. On the other hand, here is n equals 3, L equals 1, m equals minus 1. So the azimuthal dependence is e to the minus I phi, which goes through 360 degrees of phase in one revolution around the z-axis, because it's just e to the I minus 1 times phi. So that goes through 360 degrees of phase. So it goes, in other words, through every color of the rainbow, if you use colors of the rainbow to represent going from 0 to 360 degrees in phase. It goes through every color of the rainbow once when you go around in the azimuthal direction, because it's color coding according to the phase. It's color coding according to the value of m phi, in other words. On the other hand, here is n equals 3, L equals 2, m equals minus 2. That's e to the minus I2 phi. So that goes through phase twice as fast. So it goes through 720 degrees of phase, 4 pi of phase in going around the z-axis. Because in that case, 2 phi varies from 0 to 4 pi as phi varies from 0 to 2 pi. So that means this one goes through every color of the rainbow twice as you go around the z-axis. And so that's a way of encoding the fact that the azimuthal dependence is 2 phi or minus 2 phi in that u, the I, and p in there. This is m equals minus 1, so you go through every color of the rainbow. Complementary color is down here because the sign is opposite on the two sides of the xy plane in this case. Here we've got m equals 0, so you don't go through any phase as you go through. But on the other hand, you got blue versus yellow because of changes in the sign of the wave function and so forth. Here's the chemist version of the same things. The chemists make real wave functions by taking linear combinations of these complex eigenfunctions. So the chemists will make a linear combination of the m equals 2 and m equals minus 2 wave functions. They'll make different linear combinations of those to make two different real eigenfunctions that then look the same as one another, except that they're rotated versions of each other. So they create this and this. They call it xy and x squared minus, all these crazy things like that. I have to think about it. I lose track of it after a while. But anyway, I will give you a homework where you get to look at that for a simpler case than is illustrated here, namely good old the n equals 2, L equals 1, the 2p orbitals. Physicists use what we diagrammed over there before. They use orbitals where you've got L equals 1 and then m equals plus 1, 0, or minus 1. Chemists also use the one that physicists call m equals 0, L equals 1. And they call that the 2pz orbital. And then they make linear combinations of m equals plus 1 and minus 1. Two different linear combinations, one of which is oriented along the x-axis as its axis of symmetry, and they call that the 2px orbital. The other is oriented along the y-axis as its axis of symmetry. They call it the 2py orbital. And the physicists, L equals 1, m equals 0 orbital, is what chemists call 2pz because it has the z-axis as its axis of symmetry. Either set is perfectly fine. You can expand any eigenfunction, any state of the hydrogen atom can be expanded in terms of either set of eigenfunctions. The chemists like theirs better because they want to make chemical bonds and they like them looking all symmetric. Physicists like ours because we have this feeling that things ought to be eigenfunctions of L sub z. So they show up in things like what physicists like, which is like the Zeeman effect and stuff like that, putting things in magnetic fields and getting spectral line splittings and so forth. But really, both sets have their uses, and so that's all I'll say about that. Okay, any questions? Yes?
Does chemical bonding require you to use the real eigenfunctions in some way?
Well, you can only do approximate calculations is what it comes down to. And so it's more natural, it's more natural to use the ones that the chemists use because the actual wave functions are closer to those than they are to the ones that physicists use in most cases. So it's generally impossible to calculate the exact wave functions in a molecule, but you start with one way to do it is to start with single atom wave functions that are kind of similar to what you're going to get in the molecule, so to speak. And so, yeah, it basically turns out it's more natural to start with the ones that the chemists use than the ones that physicists use, if your main interest is chemical bonding. Optimal resolution notification. Oh, tragic. I don't know what I'm going to do about that. I know, I'll make it gross.
Inoptimal resolution.
Yeah, that's right. I'll show you inoptimal resolution. How about 0 by 0, bud? All right. Go away. Thank you. Okay. So, now it's time to to get dizzy because we're going to talk about spin. As a matter of that was a mistake. Okay, that really was a mistake. We're going to talk about spin. Suddenly I'm in a frame of reference where the universe is spinning.
Does it spin left or right? Or does it spin
Yes. My answer to that is yes. Okay, so the idea is when we did the algebraic approach to the angular momentum operators, we discovered that consistent with the commutation relations were not only integer values of the angular momentum quantum number, the one associated with the squared total angular momentum, but also half integer values. And that's a hint that not all angular momentum in quantum mechanics is orbitoangular momentum, that there could be another type of angular momentum, and the answer is yes, there is. There's also the possibility of what we call spin angular momentum. Spin is an angular momentum which is intrinsic to a particle. It's independent of its position in space, how it's moving, anything like that. It's an intrinsic angular momentum that belongs to the particle and cannot be altered. The closest classical analogy would be something like you've got the Earth going around the sun, so it has orbital angular momentum as a result of the fact that it's orbiting around the sun, but of course at the same time it's spinning on its own axis of rotation, so the Earth has a combination of orbital angular momentum and spin angular momentum. We can think of the electron going around the proton as having a combination, if we make a classical picture, of orbital angular momentum due to its motion around the proton and spin angular momentum due to its spinning around its own axis. However, that analogy only goes so far because you can't really picture it as literally spinning around its own axis. If you assume any kind of reasonable radius for it, you find that its surface is moving faster than the speed of light if it's to spin fast enough in order to have as much angular momentum as it's observed to have. And basically, rather than trying to dwell too much on that, I'm going to show you what the quantum formalism looks like for describing spin angular momentum. Because it's the kind of thing where you really just have to see the math and the equations as opposed to just trying to make these, analogies with how it's working and so forth. So, for spin, we'll use J as the total angular momentum quantum number. Well, actually, don't write that down. Stop writing, don't write that. Force, let's see. What we're going to do is we'll use J to represent the total angular momentum quantum number generically as opposed to what we've used for orbital angular momentum. We'll call that L. And S we'll use for spin angular momentum. So a little s for spin angular momentum. Because in general, for example, an electron's total angular momentum is a combination of spin and orbital angular momentum. So it's useful to say J is the quantum number associated with its spin plus orbital angular momentum, and L is its orbital angular momentum quantum number, and S is its spin angular momentum quantum. And then for spin, J can be either 1, 2, 3, 4, 5, 0 if it's an integer, 1 half, 3 halves, 5 halves, 7 halves, and so forth. Spin angular momentum can be either integer or half integer. So what we're going to do is write the following. We're going to write that the total spin angular momentum operator squared applied to a state which we'll label with Sm, two quantum numbers, is S plus 1 h bar squared times Sm. In other words, the label S inside this ket represents the quantum number associated with the capital S squared operator, the total angular momentum squared, spin angular momentum squared operator. And it has eigenvalues S plus 1 h bar squared, just like orbital angular momentum has L plus 1 h bar squared. S can be 0, 1 half, 1, 3 halves, etc., etc. So for spin, S can take on integer or half integer values, although for a given species of particle, it only has one specific value that can never be changed. Every electron has little s is equal to 1 half. There's no such thing as a spin 3 halves electron or a spin 1 electron, for example. So this is a little s here. It's a cute little s that's showing up there. It's the quantum number, not the operator. And the z component of the angular momentum operator applied to state Sm has what eigenvalues? It works just like orbital angular momentum. What are the allowed values of the z component of orbital angular momentum? Suppose L is equal to 2. What are the allowed values of M in that case?
Everything from negative 2 to 2.
Everything from negative 2 to 2 in steps of 1. The same thing applies here. So what if S were equal to 3 halves? What are the allowed values of M in that case? Negative to 3 halves to 3 halves in steps of 1. So that's minus 3 halves, minus 1 half, 1 half, or 3 halves. So from that standpoint, and it's because of the algebra that angular momentum operators obey, we discovered that the z component eigenvalues, that quantum number goes from minus j to j in steps of 1 in general, because we're using j to represent a generic angular momentum. Here we've got that it'll be m times h bar is the eigenvalue. M times h bar is the eigenvalue, where minus s is less than or equal to m is less than or equal to s in steps of 1. For a spinless particle, what would quantum number s be? Well, it's spinless, so what would it make sense that s is? 0, yeah. And in that case, what is m associated with it? 0, because it obeys the same kind of rules it does for orbital angular momentum. Minus 0 to 0 in steps of 1, so s equals or m equals 0 is the only possibility. So as a ket, we represent that as 0, 0. S is 0, m is 0. Again, those are just labeling those two quantum numbers values. The first non-trivial example will be for a particle which has a spin of 1/2, for example, electrons. What are the allowed values of m if s is 1/2? One half and minus 1/2. Yeah, 1/2 and minus 1/2. So in other words, there's a state which is written as, I'll put commas to be clear, 1/2 comma 1/2, and another which is 1/2 comma minus 1/2. If the spin operators represent angular momentum, then it must be true that the commutator of Sx and Sy is equal to what? What was our fundamental angular momentum commutation relation? There we go. What's the fundamental angular momentum commutation relation? So before we had it in terms of Lx, Ly commutator is I h bar Lz. These are supposed to be angular momentum operators, so they have to obey that same fundamental commutation relation that Sx commuted with Sy. The commutator of Sx with Sy is I h bar Sz and cyclic permutations.
I think you really have to hope the power back.
Yeah, apparently. Whatever, I'm not going to fight with it anymore. Now, what we'll find is the way we can get all this to work out is to use matrices to represent the spin operators. I already gave you a preview of that in the second exam when I gave you a problem where there were these 3x3 matrices that were called, I think I just called them Lx, Ly, and Lz, and I said, look at their commutation relations, and it was Lx, Ly is I h bar Lz, and cyclic permutations. And so those could serve as operators for a spin 1 particle. So that was like, a preview of things to come. Here we're looking at spin 1/2 particles. Since for spin 1/2 we read it, since for spin 1/2 there are only 2 states, spin up and spin down. And I don't really mean that it can only have 2 states. I mean that really any state can be represented as a linear combination of spin up and spin down is what I really mean. There's only 2 linearly independent basis states, spin up and spin down. We can write that 1/2, 1/2, by definition is what we will call chi sub plus, representing spin up, and it will be represented by the column vector 1, 0. This is in the S sub z basis. It won't be an eigenfunction of Sx and Sy, but it's an eigenfunction of S sub z with eigenvalue of 1/2 h bar. One half minus 1/2, spin down, is what we'll call chi minus. and it will be represented by 0, 1. And these column vectors representing the two spin states are called spinors. S-P-I-N-O-R-S, those are spinors. And the S sub z operator is h bar over 2 times the matrix 1, 0, 0, minus 1. And meanwhile, S sub x can be represented with h bar over 2, 0, 1, 1, 0, like that. And S sub y can be represented, these are not unique representations, but they work, can be represented as h bar over 2, 0, minus I, 0. And I invite you to convince yourself that the commutator of Sx and Sy is in fact I h bar Sc. So in other words, take matrix Sx multiplied by Sy, subtract from that Sy multiplied by Sx, you'll discover that's I h bar Sc. And if you do any cyclic permutation, you'll discover that you get the right commutation relations. And if I apply S sub z to chi plus, that means take h bar over 2, 1, 0, 0, minus 1, and hit it with 1, 0, or hit 1, 0 with it. Well, what do I get if I multiply the matrix 1, 0, 0, minus 1 times the column 1, 0? Well, the first component is 1 times 1 plus 0 times 0. And the second component is 0 times 1 plus minus 1 times 0. So I get back 1, 0 multiplied by h bar over 2. Or in other words, it's just h bar over 2 times chi plus. So in other words, chi plus is an eigenvector of the matrix Sz with eigenvalue h bar over 2. That's good. That says that's a state that has angular momentum in the z component, in the z direction of h bar over 2. And if I hit chi minus with S sub z, that's h bar over 2, 1, 0, 0, minus 1, multiplied by 1, 0. So the top component is equal to, 0, 1, because it's chi minus 0, 1. The top component is 1 times 0 plus 0 times 1, or 0. The bottom component is 0 times 0 plus 1 times minus 1, or minus 1. So I get h bar over 2 times 0 minus 1, but that is minus h bar over 2 times 0, 1, and that is minus h bar over 2 times chi minus. So chi minus is an eigenvector of the Sc operator with eigenvalue minus h bar over 2. So this has given us what we want. One last thing is, no, that's more than I was going to do for minus 27 seconds or whatever. So anyway, this is the start of something magnificent here, and there will be glorious further development of this next time. Yes.
How come you have SZ times? Oh.
Okay. Yeah. Right. state vector, basically. So here our state vectors are finite component column vectors instead of infinite dimensional function. A function is a column. A function is a column vector with an infinite number of components, one for each value of x. Here,